for some choice of p's, respectively, for each. And we can, actually. So it's known that 1 and negative 1 appear with the same empirical frequency for the Mobius function and the Liouville function. And the frequency of values where the Mobius function is non-zero is known to be 1 over zeta of 2. So that means we can replace the Mobius function with r 1 over zeta of 2. That is where you have, that is where p is 1 over zeta of 2. And the Liouville function with r1, where that ignores the possibility of there being zeros. We always return ones and negative ones. Now, what we find is that both of these, if both of these random walks satisfy these three conditions for the respective p and q values, there's no restriction on q other than it be greater than 1, so we satisfy the third condition. So then the question is, all of those conditions of typicality are satisfied, but can these random walks be truly typical in the absolute sense, in that they exhibit all features which occur with probability 1 for those random variables? So if 1 over zeta...
Could anything be typical in such a strong sense as that? Could probably find some feature which is going to fail for some crazy feature.
That's at least the definition of truly typical.
Yes.
So it may be an empty set, who knows? No?
So,
Yeah, that's what I'm saying. It's
Yeah,
probably
so
not
it's-
set with that definition.
Conceivable, no? But
Alright. So if these two random walks are typical, then we would learn something about the typicality of zeta. But zeta is always atypical, because we showed that it is, just the absolute limiting case in when we had the showing all the different random walks that were possible. It's inconceivable that we would have a typical walk that always chooses 1, 1, 1, 1, and so on, when there are more possibilities. So how is it that we could learn something about the typicality of zeta by studying what is typical for these two, which would be typical? And so we emerge a paradox. So then we have to conclude that both of those random walks cannot be typical, truly typical, that is. They have some conditions of typicality, but there has to be at least one condition that they fail. And so the question is, how do they fail now? So the failure has to be sourced from the Mobius function and the Liouville function, each of which are connected to the distribution of the prime numbers. So Alex Kontorovich pointed this out to us, that Littlewood showed that a certain typical feature, if exhibited by 1 over zeta q, is actually equivalent to the Riemann hypothesis, which is very encouraging for us, and perhaps also discouraging, because maybe it means we hit a roadblock. So here are my two more graphs. Here we have omega. I choose p as 1 over zeta of 2 to simulate the Mobius function. Use 2. Again, you can see that the relative frequency of these peaks is different, and that there seems to be a splitting that occurs at the top, because 1 over zeta of 2 is bigger than 1/2. And this is more pronounced in the next one, where you increase q from 2 to 3. So first we get 3 primary peaks, and each of those have sub-peaks and so on. But you can see that each one is also split in half at the top. So in the future, we want to look at how omega looks like for complex values of q. For example, q is 1/2 plus it, which are the zeros of the Riemann zeta function. We also want to see if it's possible to extend the theorem to include p bigger than or equal to 1/2. That's all.
We have time for questions. Any questions?
So in your investigations of the typicality of 1 over zeta of q, Did you find evidence for or against the Riemann hypothesis?
No. We just know that there has to be some condition that is failed. We don't know what it is, but it has to be related to the Mobius function, which is related to a distribution of primes and so on. Anyone else?
So the Cloitre product, you generalize it a lot, right?
Yeah.
Yeah.
Instead of where we began, let's go all the way. So we began where P is 1/3 and Q is 2. This all began from Benoit Cloitre's problem that he sent Professor Kiesling. That is this here. So we did generalize by saying these look sort of like probabilities, and maybe the n squared is about, maybe we can do something else with that. And we did get this as our generalized version. But also I wanted to mention that when we prove this, you'll notice this actually expresses a Levi stable law, where S is 1 over Q, where alpha is 1 over Q. Any other questions?
And speak again.